All right, so today our official speaker is Dr. Stuart Jeffries, and as always I've got a script so that I don't mess up any more than necessary. Stuart's a native of England who received his PhD in nuclear physics rather than astronomy. He's one of the many physicists here. It seems almost like astronomers are the rare people here. He received his degree in nuclear from the University of London in 1983. He then switched research paths to solar astronomy, and he's been doing that ever since. He's worked here in the United States for the last 25 years, first at the University of Delaware, then the National Solar Observatory, followed by the University of New Mexico, and now for the University of Hawaii Institute for Astronomy. He's a professor in physics and astronomy at the Institute for Astronomy, and in addition to solar physics, Stuart's research interests include image restoration and reconstruction, today's topic. So, without further ado, let's introduce Dr. Stuart Jeffries. There we go. Thank you.
Okay, good evening. So, as you see, the title of the talk is "A Picture is Worth 1,000 Words." This is an expression that I think probably everybody in this room has heard of. And if you go online and look up what its origins are, it's kind of interesting. You see that some people think it's something Confucius said, and then in fact it turns out that the most probable explanation is it was an ad campaign run by someone called Fred Bernard in Printers Inc. in the early 1920s. However, never mind what the origin was, it actually speaks volumes, right? What it says is that for us as human beings, we're very visual creatures. In fact, we get a lot of information from what we see and pictures. Now, if you doubt that at all, let's look at the last 15 years or so with the explosion in digital imagery that we've witnessed. I think nearly every one of you in here now has a cell phone, probably with 2 cameras on it, both megapixel cameras, and you just snap away and send pictures around. And this is because you can disseminate the information you want to give to people extremely easily, right? So there's a never-ending quest for resolution, okay? We always want more. So the way this has come in recent years is that we have cameras with more and more of these pixels. So we start off with a camera with, say, 1 megapixel. Maybe the space, or this is maybe 500 pixels, and we're looking at the Space Shuttle Columbia here on the launch. And this is the kind of resolution that we would get. And then we go a couple of years, and then we get some more pixels, and things improve, and we keep going. And we're just never satisfied. We always want more, okay? All right. And so what I want to go to now is something that really struck a note with me. It shows kind of where we are at the moment. And this is available on the web. And this is, a lot of you have probably seen this, right? But it's going to demonstrate some points I want to come into in my talk. This is a crowd scene in Canada just before a riot. And so what you're looking at here is a composite of about 200 and something images, digital images put together over a period of about 15 minutes. Now, the really impressive thing in my view is what you can see. So you take this and we can zoom in. We zoom in and wait, and you see, and we can keep zooming in. And then we just pan up a little bit. You can recognize all your neighbors. And you can go on and you just keep going. And it's amazing, right? So this is now about 2.1 gigapixels, essentially. 2.1, that's 2,000 million pixels, essentially, in this image. So you can see who everyone is, but a critical thing is it's blurred. Even when you pan in all the way, it's still blurred. But just to put some perspective back on this, let's go out slowly, and then you really get to see what we can do, okay? For me, that's really amazing. Okay. Now, this is with a composite, I said, of over 200 pictures. But what we have here at the IFA is we have a camera with not quite that many. I think it's 1.6 billion pixels, and we're taking pictures of the sky. And we could do a similar thing with this. We could just zoom in, and we can see amazing things. But again, at the end of the day, when you go far enough in, it'll be blurred. Okay? All images are blurred. Okay? Period. And it's inherent. So let's imagine we have your camera, okay? The first thing that stops us going to infinite resolution is the size of the aperture that we're looking through. Basically what happens is if we look at a point of light and it comes into our camera, and then it will be diffracted, and the light will spread out on our CCD into a pattern like this, which is called an airy disk. This is for a perfect set of optics now. And then the width between here and here depends on two things. It depends on the color of light we're looking at. It also depends on how big the aperture is. So you can see from here it goes as the wavelength of light over this. So if we go to much bigger apertures, this becomes smaller and our resolution improves. Okay? If we go to red light instead of blue light, it's the opposite. We go to longer wavelengths, it becomes wider and we see less resolution. So these are two fundamental limits to what we can expect in an imaging system. Okay? So the next one is if we think about how we look at look at objects. Okay, basically we have light that comes from some source, say the sun, comes down, hits the grass over there. Then the light that's reflected is all that's not absorbed. So everything except green's absorbed, and it comes back to my eye. And then if it was to take a direct path, I would see a very beautiful image of the grass that I'm looking at with whatever resolution my eye lets me have at that point, whether my pupil's dilated or contracted. But that's not what happens. What happens is we have an atmosphere in between. And so basically the rays get bent a little bit. And so what that means is by the time it gets to my eyeball and focused on the back, the information is not where it should be. It's in a slightly different place and the image becomes blurred. We also get blurring from optics. Optics are never perfect. Okay, so basically images are always blurred. So what do we do in this quest for continuing resolution? All right, so tonight I'm going to talk mainly about two topics where we're interested in this, or two subjects I mean. One is astronomy and one is surveillance, okay? And that's because it's something that's dear to our hearts here in Maui. We do a lot of research on that. And in both of these research areas, we're always looking through the atmosphere. So I wanted to give you some idea tonight of just how badly the images are that we're trying to unscramble when we look through the telescopes and things like that. Okay, so we start off, and what we're going to imagine is that, so in the Earth's atmosphere, what we have is we have pockets of hot and cold air, basically, okay, and these refract the light so differently. So as the light comes from a distant source, it comes in, it gets bent a certain way, and if it hits a different temperature air pocket, it gets bent another way. And then what we can think of is in the air that these pockets, this is a naive description, but they're roughly of some order of size about this, okay? So that means this would be the maximum size of telescope I could use without suffering any blurring from the atmosphere. If I go bigger than this, I start seeing not only the blur from the telescope, but the blur from the atmosphere on top. So if we take a fairly large telescope now, and we think about, I've got some cells of this air about this big going across the front, and I look at two of them, then the light that comes into these two can basically interfere. I don't know when you were at school if you did it's called the interference experiment where you would just interfere two beams of light and you would see this. And so you might see a pattern like this. Now if I take this and I go to 3 patches in the thing, then the pattern becomes much more complicated. And of course you can imagine as this fills in, this becomes very, very complicated. So once again, what's happening is a single point of light is coming in, and this is how it gets spread across the image. So if I'm looking at a picture of, say, your face, each piece of your face, the information from that will be spread like that. And so at the end of the day, I won't be able to see very much. Okay. Conditions on Haleakala. This is what we try to look through. Basically, what we're looking at here on this side is some measure of what the atmosphere is doing with the size of these cells. Okay, and this is the time of day. So you can see so when the number's large, this means it's very good for us to see things, and when it's small, it's really horrible. And you can see there are large fluctuations. And then during the day, it becomes a very, very, very difficult problem to do. So what kind of spreading do we get? So I'm going to imagine that I'm looking with a 1.5 meter telescope, 1.6 meter telescope now, in visible light. I picked this one because it's one of the ones on the mountains that the Air Force use, okay? So right around in the night time, in the middle, typical conditions, every point in my image will be blurred by something that looks like this. That's not so bad, you might think. You might still be able to see things. If I start looking at some of the worst conditions, or perhaps some of the best daylight conditions, every point now gets spread something like this. This starts to become pretty tricky to unscramble. And if I'm looking in the day, it goes like this. So the conditions get worse very quickly. Now, you can see that these all depend on the diameter of the telescope. So if my telescopes get larger, okay, then for the same conditions, if I had a small telescope and a large telescope, the small telescope will not suffer from the distortions from the atmosphere anywhere nearly as badly as the big one. But it doesn't have the resolution of the big one. So there's always a trade-off, okay? So what is the impact on the images that we get? So this is just a model now, a mock-up model. This is the Hubble Space Telescope, and this is what it would look like if I was to look through a 1.6 meter telescope and I had no atmospheric distortion. It's called the diffraction limited. So and this is actually in a red wavelength. So you can see here, immediately we've lost a lot of resolution because the size of the telescope, and also because I'm looking in a red wavelength. So if I look at benign turbulence, that's something where it's some of those conditions that are hardly ever met. Then the degradation, remember every point of light in this gets blurred by this, comes into something like this. So I still get to see in some sense, some morphology of what I'm looking at. But if I come to moderate turbulence, not even the bad one, I've pretty much lost the image, okay? So we're faced with a problem that we have data like these and we have to ascertain what's underneath here. So how do we go about that? Okay, so I'm going to show a little movie now about something called adaptive optics. This is something I found on under the Gemini project page, and it has a beautiful description of adaptive optics. Basically what we're seeing here is the Gemini telescope just opening up, and in a second we're going to see, so here we go, the telescope's going to point at some target now, and then the simulation is going to show light coming from some distant star, and the light comes down, hits the primary mirror, reflected off the secondary mirror, and then comes down into the lab. In the lab it comes into this box where we have something called adaptive optics, which is going to compensate for these distortions that we see in the Earth's atmosphere. So here we go. Basically the light comes down, gets reflected off some mirror here, gets reflected off a mirror here that lets some of the light through onto a sensor down here, and then this goes off to be imaged on the camera. So the light that's coming in from our source is distorted from the atmosphere. You can see the wavefronts here are all distorted. As it comes down to the bottom here, it comes onto this sensor which detects the distortions, basically, comes up to the mirror here, and then warps the mirror to undo the distortions. I'm going to play that again so you can see. Okay, so we have to wait. So basically, as the light comes in, the mirror knows what it needs to do, how to be offset in order to flatten the wavefront to go into the focal plane optics, which are then image onto the cameras. Now, one of the things about adaptive optics is that with these mirrors, you can only have so many segments that move to compensate for the distortions. So if the distortions in the light are not too bad, you can do quite a nice job of compensating. But as the distortions get worse and the frequency of their spatial frequency gets higher, you don't have enough of these pistons to move up and down. So this is the deformable mirror here, and this is something called a Shack-Hartman, it doesn't matter, which detects the wavefront and sends the signal back up. And as you'll see, the wavefronts come in here, distorted at this point, then they get sampled, comes in, closes the loop, makes the mirror distort, and then once they come off here, they're flattened. And then once they come back over here, you'll see in this little cartoon, basically the image goes from this to a beautiful airy disk. Okay, so but what we have to remember is even the best adaptive optics at the moment only have a certain number of these actuators, they're called, that can actually do things. So this is a little video now of something taken with the university's adaptive optics system called Hokupa'a, and this is just a little demonstration of how well adaptive optics works. Basically, this is looking at a triplet by the looks of it, and of course you can barely see anything without the adaptive optics on. As soon as it comes on, you can see the 3 stars. So this is real data now from Hokupa'a, And if we move on here, this is something now that's come from, it's just looking at the sun with adaptive optics. And so this is from a telescope in the Canary Islands. And this is with the adaptive optics off, and this is what we would see. And as soon as we turn the adaptive optics on, it becomes vastly improved. But I want you to notice there's still this morphing across the image. And this is because we don't have enough actuators to compensate for all of the distortions. So this is still blurred, okay? But we've done a great job of improving the resolution, but it's still blurred. Okay. Okay, adaptive optics correction is also, I mean, outside of astronomy, is also had a lot of research done in the area of human vision. I mean, all of our eyes, basically, okay, we have some aberrations in our eyes, and that's why we wear glasses. So what in human vision, what they're doing is they're using adaptive optics to actually look at our eyes, to see, you know, the rods and the cones, and to be able to perhaps diagnose illnesses and things like this early. But also, it will enable us soon, as a big, to fabricate glasses that are actually a perfect prescription for you. Okay, so at the moment, you only get, in the glasses you have, only have the few low-order aberrations being taken out. But eventually, you'll be able to have them that absolutely custom. So, okay, as I said, AO has limitations. And this is just to give you some idea of how the limitations go. Basically, when conditions are good, the adaptive optics does well, and you get a diffraction-limited image. When they start to deteriorate, they still did quite well, but you can see it's starting to not be able to handle everything properly. And as soon as you're down here, it does nothing, basically. Nothing that you can discern with your eye. So if we have these problems of trying to look at any objects in the sky where the turbulence is high, adaptive optics only helps us a little bit. It doesn't really do much for us in the long run. So we have one last card up our sleeve. It's digital image restoration. Okay. Now, all of you have seen CSI and things like this, where they do these amazing things. Okay. They do these things where they say, "Oh, play that again. Stop." And they look in and they say, "Zoom in that corner." And you go in. There's this blocky thing. Okay. Enhance, and all of a sudden it becomes magically 10 times better. Okay. Improve the resolution, and then, oh, I can see in his sunglasses the registration plate of the car we're looking for. All right? Now, if I could do that, I would probably just, go and cash in my chips now with one of the big agencies like DARPA and then just retire, okay? But anyway, so restoration and reconstruction are very important these days. And actually, it's kind of ironic how a lot of the research got started with this. It was the Hubble Space Telescope. Fired things up. We put a telescope up there, and then it's the optics aren't so great, and now we've got to figure out how to deal with it because we've got a little bit of egg on the face. All right? So there was a tremendous amount of work done in image restoration in the early 90s. That's also with medical imaging. There's also been another input into this, and now we have some algorithms that can do some pretty amazing things. So the basic premise is this: we observe some target like this, which is all blurred. The basic premise is, we know something about how it was blurred, okay? If we do those, then we can take a little bit of math and physics, and we can unscramble it, and we can get the thing we're looking at. That's the idea. Okay, what's the fly in the ointment? There's a big fly in the ointment. Okay, we don't really know this, especially with the atmosphere, okay? And even with anything like, almost any situation you can think of, you don't have perfect knowledge of this. So it's always going to be blurred. So the challenge is, okay, I'm given this. I have no idea what that looks like, and I have no idea what this looks like, but I've got to figure them out. This is called blind restoration. Now, in the early 90s, when people figured out how to do this, and actually when I gave some of my early talks, it was like it was a black art, and I was preaching something that was really not too savory. But there's been a lot of work done in this area now, and it's a problem we can solve. And how do we solve it? Okay, like it says in this box, physics and math. So what we have to do is we have to take what we know about the whole imaging system, and we use it as constraints. So what we're after, remember, is I'm given that. I now need to reproduce this and reproduce that, only knowing this. Well, what do I know about this? Well, I know whatever I get for this and this, when I blur this with that, it has to give me this. Otherwise it's not right. That's the number one thing. And that's an important one. The next thing I know is I'm looking at light, incoherent light that's coming, okay? So it's always going to be positive. I can't imagine how I'd ever get negative light. So I know that this is something positive, and I know this is something positive. Sometimes we have knowledge about the extent of the object. So let's imagine I'm looking at the blurred sun. Well, I know the sun's round, so I can say I know something about the support. That I don't know exactly how big it is, but I know it's smaller than this. All right? So this is, again, more information that I may have. And then there's other types of information as well. And maybe while I've got the adaptive optics running, the detector I was showing you that was measuring the wavefront, that was helping with the correction, well, maybe that actually measures some things about the wavefront that's not being corrected, and I can take that and use it, etc., 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 okay? And this is what helps us solve the problem. However, the best approach of all is we always want to use adaptive optics and image restoration, okay, if at all possible. So I'm going to show just a few examples now, and then, to give you some idea of what we can do. So this, right now, this is the real movie of the granulation on the sun's surface, and this came from just doing image restoration only, okay? Pretty nice, right? I mean, we get to see the granulation, the boiling, we can compare it with models that we build, and numerical models, and we see things look good. Here's something that's come from the NST telescope in Big Bear recently, which is a 1.6 meter telescope, where they've got adaptive optics on, and they've performed image post-processing. I think you're looking at probably one of the finest detailed images of the sun ever taken. All right. In fact, one very similar to this was voted last year by National Geographic to be amongst the top 10 images of space-based targets, and they said that they thought it was considered the best solar image ever. Wow. But I mean, you can get some idea of the level of detail here. Okay. Now this is also exciting because this is a 1.6 meter telescope. What have we got coming to Maui? 4. We have 4. Now, if you remember, at the beginning of the talk, we said that the resolution goes as d over lambda. Okay, it depends upon the diameter. So as soon as we go to 4 meters, the resolution that we're going to be able to see in the images is going to blow this away. Wow. Aha! Maybe. Okay? Because what's the caveat? As my diameter goes up, my turbulence problem gets worse. So now I need better adaptive optics. And so what's coming with our 4 meter telescope will be the next generation adaptive optics with many more actuators. I don't know the exact number. Anybody know? But it's at least twice the number we have now. We have about 1,000 actuators on the best AO systems at the moment, okay? So it's going to be a lot more than that. But even then, we're still in trouble because remember, AO, adaptive optics, doesn't cut the whole cake for us. So we're going to have to use image restoration. But at the end of the day, we're going to be able to see things, if we do things right, on the sun with a resolution of about 100 to 150 kilometers, somewhere around there. And to give you some perspective of that, the Earth fits in there roughly. Okay? So that's, we're going to see. Planetary, now this is something we did in planetary astronomy several years ago now. This was just, this is an image of Io. This is a moon of Jupiter. This was a ground-based image, and this is after the image restoration. Before it just looked like a blob. What was nice is we were able to study this, and it was actually, we were able to look at Loki. It's one of the volcanoes on Io. We were able to study this over time, and there's no way we could have done it if we hadn't had image post-processing, because we couldn't even see Loki in the things. Okay, now I'm going to move away from astronomy a bit to surveillance. Over the last decade, I've been doing a lot of work for the Air Force here because we have a big presence with surveillance, okay? So let's look at some of this. One of the things that, this is a different type of surveillance, is it's called something about increasing the depth of focus. Now, if we take an image, if we take a picture of people in this room, okay, it'd be like this box of crayons, okay? Basically, the people at the back would be out of focus if I was focusing on these. This is in focus, out of focus again. All right, so how do I get round that? Well, along with some colleagues at Wake Forest about 7 years ago, what we did is we came up, there's a notion out there about using something called a cubic phase mask, which is not our idea, but it's a very good idea. And basically what that does, it makes everything out of focus like this. We take this with image restoration now. because the way this image is blurred is the same across the whole image, and I know how it's blurred. So from that, I can do this. All right. So now everything's in focus. Why is this exciting from surveillance? It's because of retinal scanning. Okay. There's a big need now. Okay, with biometrics and everything. Is if I take a picture of this room now, I want to be able to see everybody's retina and then identify you. Okay. So if I take a picture, and this is with a cubic phase mask, and then I restore it, I get this. And this is a picture taken with an in-focus camera. So you can see that there are great steps being made towards retinal scanning. So the thing is, you don't have to put your eye right like this. If you want to go into the bank deposit box or something, you'll just be able to look up at the camera. But the reason that it's really wanted is just for scanning people with disguises and things like this. So this is one area that this image restoration has helped. Now we move to space surveillance. This is something I've shown a couple of times, but I like it. This is some imagery taken here at Haleakala of the Space Shuttle Columbia just before its tragic re-entry in 2003 when we lost the 7 astronauts. Okay, and what NASA wanted to know is they said, can we tell from this imagery if there was any structural problems with it? And so this is the imagery. So we use this blind restoration method, okay, and this is no adaptive optics on this, and this is what we were able to come back with, okay. So it's quite nice. Unfortunately, we couldn't see enough detail because the theory was that it was along this edge that there may have been some damage. But to give you some idea of the level of detail we got from that, this is a picture of the Columbia on the launch pad. This is a picture of it as it rotated and came over us, and we can't quite see the words Columbia here, but not too bad. Okay.
And how far away is it?
Oh, with that at the altitude, it's 140 kilometers. Yeah, yeah. So, okay. So the next thing is monitoring space debris. Okay, this is just a cartoon that I've stolen off the web. Okay, but it's an artist's rendition of what it looks like in space for us now. Okay, there's debris everywhere, and so it's one of the charges for the Air Force is that they're interested in tracking all of this because obviously this can affect our assets in space, such as geostationary satellites. It's dangerous for astronauts, etc., etc. So we want to know where everything is. So here's an example that we did recently of some images of SEASAT. This is an interesting satellite. It was the first remote sensing satellite that was launched in 1978. Okay, it had a very short lifetime. There was an electrical surge on it that put an end to it, but it's still floating around up there, and it needs to be tracked. Okay, and so from these images, which don't have adaptive optics or anything like that, and I think only from 9 of these images we were able to reconstruct this that tells us a lot about its integrity. And the nice thing is, here's a cartoon. If you actually look at this cartoon carefully, all the details here are actually, there are no artifacts. Okay, so we're able to do some nice job of tracking these targets. The next thing that we've been interested in is we're interested in imaging satellites 23,000 miles away, the ones that are in geostationary orbit. These are our communication satellites. If the communication satellites were to go away, we'd be in big trouble now. Okay, we rely on them so heavily, no more, especially our defense. The US has a superiority over other countries because of our GPS system and things like this. So, about 4 years ago, I mean, they're so far away, they've never been imaged. About 4 years ago, along with some colleagues at the MMT in Arizona, we took, which is the 6.5 meter telescope, we took some imagery of this Canadian communication satellite called Anik F2, and there's a cartoon to show you what it should look like. And this was the observed image before AO came on. This was the image when we had AO, and then we took this, and I want you to pay attention to all the blur here, and we were able to get this from the image restoration. Now you might say, wow, okay, all right. But this is what was cool. From this, by measuring this length, we were able to calculate the pitch. It's in the sky. And they didn't tell us what it was, but we told them what we thought it was, and we were within 1 degree of what it should have been. Okay? And not only that, because of this, we were able to measure the reflectivity of this, of the solar panels and everything, and this enabled us to do some modeling, which I'm going to show you now, of what can we see in geostationary orbit. What's the smallest... Oh, hang on. Okay, I'll come back to that in a second. All right. Imaging satellites, okay, during the daytime. This is the big problem, all right? We can't see them. There are a whole class of satellites that pass over that we'd like to see, but we can't see it during the daytime. So the challenge is we want to see this, but this is what we observe. And this was actually in the poster, right? After I put it in, I thought, well, nobody's going to come to the talk because it's just a blank white sheet. But this really is a simulation of what you would see in the daytime, okay? Now, so we use these blind restoration methods, but we also use, so we've got adaptive optics, we have the adaptive optics wavefront sensor, and we use the information from the wavefront sensor to tell us something that enables us to unscramble this. And what you see here on the bottom, this is actually using the wavefront sensor data to tell us about what the winds are doing at different heights above our observation. So this here is telling me that I've got a wind in this direction that's going very slowly. This is my ground layer wind. It's about 5 meters per second. These two are showing that I've got high elevation layers going at about 25 kilometers and 30 kilometers in 2 different directions. We use that information along with a simple idea that the atmosphere over maybe a hundredth of a second doesn't change. It just gets blown across by the wind in front of our telescope, okay? We use that in our image restoration, and by doing that, we're able to turn that into that. Okay, so we've just made a breakthrough now in this daytime imaging, and so we're actually now the Air Force is just collecting data for us to verify these. How small an object can we see? Okay, this is in geostationary orbit. So why am I even concerned about it? So first of all, anybody have any ideas what the smallest satellites are, except for Joe and Stan? Anybody have any ideas what the smallest how big are the smallest satellites up there? Are they? I mean, to give us some perspective, a communication satellite, 50 meters. Okay, they're big. So what do you think? Do you think 60? Yeah, Coca-Cola can actually.
Really?
Yeah, Coca-Cola can's the smallest one. So there's a concern, right? Because what you can do is if I have a communication satellite and I have a Coca-Cola can that's just displaced off a couple of 100 meters or something, then it may have the capability to knock my satellite out of orbit if it's tactical or whatever. So we're interested in knowing these things. So how small? So we did a study for how small we can see things. And these show observations at 2 wavelengths, blue and red. Might be red and blue, I don't know. So we used the same tricks as we've been doing now, and that's what these are all simulations. That's what we were able to come back with. There are a lot more satellites there. This was what the simulation had, but from this we determined that we can actually see laptop size at this moment, but we want to see this. Actually, we want to see that if we can. All right, so we're making good progress towards seeing these smallest satellites, but I still think the size of this projected from 23,000 miles is not bad. Okay, coming to the end now, we're talking about looking through translucent objects. This is something we did about 8 years ago now, and here we have a very different problem to what we've been discussing. Here we have something like clouds that we're looking through, and the light coming through that takes a much more tortuous path than normally, okay? So you have 3 sets of photons or light coming through, basically. You have something called the ballistic ones. Somehow, that by a miracle, they get through, and they preserve the information on what they've reflected off to your instrument, okay? There's only a few of them. They arrive quickly. Then you have some that they call snakes. They take a bit of a tortuous path, and they get there a little bit later. But most of them just get reflected around everywhere, basically, okay? And they're called diffusive ones. And so now, when this light arrives at my detector, it's lost all knowledge of where it came from, almost. So how do I unscramble that? Okay, so this experiment was or this research was to see, can we identify planes in clouds? Okay, and so we started looking at it, and the interesting thing here, it turns out that clouds and female breasts have the same optical properties, essentially. Okay, so we got phantoms from the hospital, breast phantoms, and we put toy planes in the breast phantoms, and then we irradiated it with infrared light, and we looked at what we could get. And so this is the type of image that we got from this. Once we did the restoration by backing out what we believed in things, we get this sort of shadow type thing here of what was in the center. Now, you may say, well, that's not that great to get this from that, but there are some subtle things here. We were, as part of estimating this, we had to get the depth. We had to estimate the depth. We were able to estimate the depth. It was in this 5 centimeter thing. It was 2.51 centimeters to the edge, and then that's what we measured. So what's the upshot here? Well, I'll give that to you later, okay? All right. Now, this is why it was useful. So, friend or foe, okay? There are 2 pictures taken of irradiating a cloud with some infrared light and the reflected returns of 2 planes. So if you were a general, you'd have to make a decision, friend or foe. So you run it through the restoration. Friend. Even this information is enough to tell it's the F-18, this is F-111, the difference, okay? So even though it's imaging in a different kind of mindset in some sense, the information that's being brought back is really large. The methods can also be used for underwater imaging. All right, now the implication of the work there is X-ray mammography. All the ladies in here are well versed with the nasty nature of a mammogram. Okay, you've got several things: physically unpleasant, irradiated with X-rays that you really don't want to have. Okay, and if they see a lump, is it benign? Is it malignant? We don't know. Let's do biopsy. That's fun. Okay? So there's something now called optical mammography that has been around for a long time. Okay? And so in optical mammography, you can get, you take pictures in different light, and then even though the resolution's poor, you can actually differentiate between benign and malignant. Okay? And also it's a much more pleasant experience. Basically, you lie on a bed like this with a cup, and you just have something like a laser from a CD that scans with detectors the other side, and you get these images. So this has been going around for a long time, but about 8-9 years ago, there were several sets of work, ours and several others, with this digital restoration, and now taken this a step further into maybe it will be reality one day and in the hospitals, okay? Because now, in principle, we can see a sort of shadogram of the tumor or cyst or whatever it is, and you can tell whether it's benign or malignant without biopsy. Okay, so we're coming to the end here. Take-home points, okay? High-resolution digital imagery. It plays a big role in society today, okay? We just can't get away from it. What I find really fascinating is we're seeing things now we've never seen before, and there's more to come, a lot more to come. And in fact, in about 8 years, or 5 years from now, when you're listening to somebody here from the ATST talking about first light results, I guarantee we're all going to be blown away by what we're seeing on the sun, for sure. Okay, thank you.
What's the application for a COPE-CAM sign satellite?
Oh, well, they do many things. I mean, you can put small experiments in things like that. But I mean, the one that's of concern, right, is if they're tactical. So I mean, all you have to do is perturb the orbit of your communication satellite, and you've just knocked it out basically. But you can. Joe knows more about this than me, but you can put, what is it, about 10 centimeters squared. You can get some interesting experiments in there, right? You can. So there's a lot of universities now actually launch these CubeSats about this big and send them up. The Chinese put a lot up there too.
Summation of it. Are you using that throughout all this, or are you just recording the image and stack them on top of each other?
Aha. Good question. No, you can't just stack images this way. Most of the ones we do here is we have to freeze the atmosphere. If you freeze the atmosphere, it maintains information all the way to the telescope passes out to the diffraction limit. All that information is maintained. As soon as you start just summing them, it goes to something called the seeing limit. It goes to the amount of information that's passed by the cells that we were talking about. So what you want to do is you want to do all your processing on the very short exposure images, not long exposure. Okay, especially when you're looking through the atmosphere. If you were to just, set it for 5 seconds looking at some star or something, it's going to be really, really blurred. What you want to do is image about every 10 milliseconds, take them all and do the processing on that, and then you will see a lot more information.
So you post the adaptive optics, you can't sum them together.
Well, the adaptive optics you can sum together, but okay, so with adaptive optics what you'll get is, if you look at the way the light spreads, it's a very sharp core, and then it has this halo around it, okay? So and it depends on the level of the halo. So it depends on what you're looking for. If I see something with high dynamic range, let's imagine I want to see an extrasolar planet next to a really bright star. I may need to, see a change in intensity of maybe 1 million. This is huge. Right? I can't do that if I've got this halo of light that's being sprayed around. So the way I do it is I take these short exposures, I model them very well, through the wavefront sensor data. And so this is, when I say the wavefront sensor data, this is the wavefront sensor data contains information that's not being used by the adaptive optics. When you extract that, then I can clean up all those individual speckles, they're called, the patches of light, and I can do a much better job than I can ever do if I try to do the whole halo in one shot. Yeah.
I seem to remember reading about some of the original adaptive optics where they shot a laser, maybe separate them, but they shoot a laser in the direction the telescope is pointed, and then that reflected light would tell you the state of the turbulence, and that was used to process. But is that no longer done?
No, that's true. It's still done. In fact, I only glossed over adaptive optics, but you're right. There are lasers, and there are there are several types. One is called a sodium laser, and what that does is it reflects light off a layer where meteors have deposited sodium in our atmosphere at about 90 kilometers to 100 kilometers above. It goes up and it reflects back down, and we get a measure of the atmosphere. But unfortunately, it's not what we want because of something called the cone effect. Well, an easy way to see that is if I have a layer of atmosphere right on my telescope here and another layer, say 11 kilometers, and I've got something that's returning light from here, it makes a cone through there. But my target's up there, and that makes a slightly different cone through the upper layer. And so the resultant distribution of light depends on how the summing of the perturbations as it goes through. And so the two things don't see the same paths. So it does quite a good job, but there are some problems with that. Another one, they do something called Rayleigh scattering. They just use blue lasers, and that you get backscattering, and they just gate. They only look for very short times. And one of the things that they're doing now is that you have rings of these guide stars, and the rings of the guide stars, they put 4 or 5 up. That actually overcomes this, what's called cone effect. But of course, this is a really complicated system that you're talking about now. Yeah.
Virtual World. NASA's Lunar Micro Rover Project website says that they are working on interstellar missions for planetary surfaces. Will lunar VLBI, very long space-like interferometry, achieve imaging of exoplanet ozone, signaling life, etc., and this, in the amount of water before space VLBI?
Well, interferometry is something that we haven't touched on here. It's another extension. I've been talking about filled aperture here. So interferometry is where I have sets of telescopes, and I have to interfere the light. The short answer is I don't know. This is not my area of expertise. So I can't answer that. Yeah.
Can you use the same camera like Pan-STARRS camera to look up in the sky in the daytime?
Please repeat the question so that people in the virtual audience can hear.
Can we use the Pan-STARRS camera in the daytime? Maybe. I think that the problem with using the Pan-STARRS camera in the daytime is that we'd have way too much light for it, is my guess. But I guess that if we were to look in a narrow band of light, then I see no why not. The larger the camera, the slower it takes to read images out. And remember, one of the things that we want to do is we want to read the images out very, very quickly. So we're trying to read out at maybe 100 frames a second or more. And so I'm pretty sure Pan-STARRS doesn't go that fast.
None of our filters will allow that, and our camera is tuned in such a way that would completely saturate it.
Yeah. Yeah.
We have a bad problem on full moon nights.
Yeah, they learn the sign. Okay. All right. Well, thank you very much.
Nobody slept. That was full attention.